Hi, welcome once again to Math as a Second Language. And today we continue what I thought was a fascinating discussion last time in terms of what it means to multiply two large numbers using place value. And in the same way that we introduced unadding after we introduced adding, today we're going to talk about unmultiplying as opposed to dividing. And I think the easiest way to see that is what they call, I think they call them number bonds in today's literature. I'm not sure. I think that's what they call them. It doesn't really matter. It goes something like this. Suppose you wanted to make a fill-in-the-blank statement from the given fact 3 plus 2 equals 5. There are three ways that you can do it. One way is to say 3 plus 2 equals blank. Another way is to say blank plus 2 equals 5. And a third way is to say 3 plus blank equals 5. This is the one that is usually straightforward. This is what you see is what you get. You see a plus sign and you're adding. This would be 3 plus 2 is 5. It's an addition problem. What happens is when you leave out one of the add-ins, one of the numbers you're adding, in other words, you have a number plus the sum but missing a number, that's what we refer to as unadding. And every time you have a fill-in-the-blank that involves addition, you have two blanks that involve unaddition. Namely, I can either replace the 3 by the blank or the 2 by the blank. And both of these would be a form of unadding. The same thing can be applied to multiplication. If you want to make a fill-in-the-blank from the number fact 3 times 2 equals 6, you can say 3 times 2 equals blank. You can say 3 times blank equals 6. You can say blank times 2 equals 6. And so what happens is you get, again, this is multiplication. And because one of the multiplying numbers, one of the factors is missing, these are called unmultiplying. Well, by me they're called unmultiplying. By everybody else they're called dividing. And notice the number bond here, there's two separate things here. In other words, when you look at 3 times 2, are you talking about 3 objects at $2 each or 2 objects at $3 each? For example, 2 times 3 will always be 6, but what the 6 modifies depends on what the 2 and the 3 modify. If I go into a restaurant and order 3 2-minute eggs, and the waitress brings me 2 3-minute eggs, it's the right number of egg minutes, but it's not what I ordered. But at any rate, this is what I want you to do, is to visualize division as a form of multiplication. When you see something like 6 divided by 2, what you're really saying is the number which I have to multiply by 2 to get 6 as the product. Now, with that in mind, let's go back to our discussion of last time, where we were talking about, I believe, the multiples of 13, and we were talking about a salesperson who was selling pens at $13 each, and we asked the problem like, how much money would he make if he sold 234 pens? See, here's the thing. Let's look at the number fact, for example, 4 times 13 equals 52. I can look at this as saying, if I sell 4 pens, I made $52. That's multiplying 4 times 13. I can also say, in order to make $52, I would have had to have sold 4 pens. Do you see the subtle difference? So let's suppose now I'm the salesman, and instead of knowing how many pens I sold, I now know how much money I made. And I'll make up a number here. I took in $2,821, and I want to know how many pens I sold. Now, one way to do this, as we mentioned last time, is I could just make this table and go all the way down. See, last time we said we'll go all the way down till we get to the 234th line. This time we say we'll go all the way down until the total amount that he made is $2,821. And again, can you see how tedious that is? Well, the average student says, that's no problem. I'm not going to worry about that. I'm just going to divide 2,821 by 13, because after all, isn't that what we're saying? How many 13s does it take to make 2,821? And I think you all know the mechanical recipe. You say, we used to call them gazinta problems in my day. 13 gazinta 28 twice. 13 times 2 is 26. You subtract the 26 from the 28, you get 2. You bring down the next number. You say 13 goes into 22 once. You subtract the 13. You get 9. You bring down the 1. You say 13 goes into 91 7 times. How do I know that? Well, I know the table. All I have to do is know the multiples of 13 through 9 because the place values, the denominations, take care of all the rest. And you say, how will I check this? If this is the right answer, what should happen? If I multiply 217 by 13, I should get 2,821. So I do that, and I get 3 times 7 is 21. Put down the 1, carry the 2. 3 times 1 is 3 plus 2 is 5. 3 times 2 is 6. 1 times 7 is 7, 1 times 1 is 1, 1 times 2 is 2. And if I'm making this sound like a rote drill, that's exactly what I want to do, because that's how many youngsters do the problem. It's a recipe. Anyway, let's go on. So you say 1, 7 and 5 are 12, carry the 1, 1 and 6 is 7, and 1 is 8. I get exactly the right answer. In other words, what number goes in here? It would be 217. Now, if you were to ask the average youngster, or even the average oldster, why does this recipe solve this problem? They say, I don't know, but it does. Now, in the old days, this was fine because there were no calculators. The important thing in the old days was to make sure you got the right answer. You didn't have to understand why it was the right answer, though that would have been nice. The thing was, don't make a mistake. It's going to cost you money. It's much the same way. It's not quite the same thing. I can drive a car, not as well at my age as I once did, but I have no idea how the car works. I know I can make the car go faster by stepping on the gas pedal, but why does that work? I know if I step on the brake, the car will stop, but why does it do that? And the answer is I don't have to know that unless I'm repairing cars. And in a sense, if all I'm going to have to do is get the right answer, I don't have to know why it works. I just have to be guaranteed that it will work. So let's find out, first of all, why it works. And secondly, by explaining why it works, how simple and understandable this algorithm is for division. This is a fill-in-the-blank problem. I know that each pen that I sell gets me $13, and I want to know how many I have to sell in order to make $2,821. And I'm leaving out the dollar sign because I don't want you to get the feeling that it has to be a money type of problem. In other words, these are the adjectives that we're working with, whether we're talking about books per carton, dollars per pen, whatever it happens to be. So here's what we do. Knowing that 13 times 2 is 26, remember I'm saying I'm going to know the first 9 multiples of 13. I know that 13 times 200 is 2,600. What that tells me right away is I must have sold more than 200 pens, because if all I sold was 200 pens, I only would have made $2,600. And I know I made 2,821. By the way, how do I know I didn't sell as many as 300 pens? Well, 13 times 3 is 39, so 13 times 300 would be 3,900. In order to have sold 300 pens, I would have had to have made $3,900. So by the way, just by this one observation, I already know that I sold more than 200 pens, but less than 300. But I want a better answer than that. So I say, okay, let me subtract off the $2,600 that I would have made if all I sold was 200 pens, and see how much more that would leave me with. So I subtract the 2,600 from 2,821, and I get 221. Now, from 221, I see that I don't have enough to take out another bundle of 100, because 13 times 100 is 1,300. I have enough to take out a bundle of 10, because since 13 times 1 is 13, 13 times 10 is 130. So that tells me I can take out at least one bundle of 10. I can't take out 2 bundles of 10 because 13 times 2 is 26. That means that 13 times 2 would be 260, and I don't have 260 left. But I can take away 10 more. If I take away 10 more, in other words, I now know I sold at least 210 pens, but that would still leave me with what? I subtract the 130 from the 221. I have $91 left to account for. From the table that I made, I see that 13 times 7 is 91, so I know I have to now sell 7 more pens. If I do that, that takes care of all the money that I took in. How many pens did I sell altogether? 200 plus 10 plus 7. Now, does that look a little bit more logical? Can you see what really happened here? Can you visualize what went on here? Let's call this method number 2. Let's call this method number 1. Is it fair for me to assume that you're more used to seeing method number 1 than method number 2? But that by the same token, method number 2, even though you may not have seen it that often, looks easier to follow than this sort of mystical formula over here. Now, let me show you how by doing this, showing the why, this suddenly becomes trivial, believe it or not. Look, when I said 13 goes into 28 twice, I put the 2 over the 8. Now, the 2 is always 2 as an adjective, but the position I put it in tells you what it modifies. Where did I put the 2? I put the 2 over the 8, so that even though it looked like a 2, it was really what? 26. 26 what? 2600. Okay? So far, so good? Now I subtract the 2600 from the 2821. I get 221 left. This 1 over here was put over in the tens place. It represents 130. Now here's what I want you to do. Look at this, and look at this. And other than for the position on which they're in the paper, can you see any difference? Exactly the same. In other words, the few seconds that it takes to do this thing as a mystical magic formula, leaving out the zeros. How long did it take me to put these zeros in here? Not long. But those few seconds are the difference between a student understanding what division means, what unmultiplying means, as opposed to just memorizing this as a ritualistic tool. By the way, there's something else nice about this. First of all, to make the transition from my visual method to the recipe, we could do it this way. When we put down the 26, put down the 2 zeros and just write 200 over here. In other words, this tells us that if we subtract 213s from 2,821, we still have 221 left. Now, when we say that 13 goes into 22 once, that means the 1 is in the tens place. That accounts for 10. Okay? There's your 130. I did this in a different color so you can see how they match up. Now there's 91 left. I know that 13 times 7 is 91. So what do I see altogether? I could take out 213s, then 10 more, and then 7 more. And later on, what you could do is just say, why don't we bring the 1 down and the 7 down, and we can eliminate putting in these zeros, etc. It doesn't really matter. But do you see the transition? Now here's another interesting thing. If I multiply 217 by 13 the usual way, by putting the bigger number on top, I wind up with what? I did previously 3 times 7 is 21, carry the 2, 3 times 1 is 3 plus 2 is 5, 3 times 2 is 6, 1 times 7 is 7, 1 times 1 is 1, 1 times 2 is 2. I get the same 2,821. It works. But there's no connection between what I did here and the numbers I'm seeing here. And the reason is I wanted to see how many 13s it would take to make 2,821. What I did here is to see how many 217s it would take to make 2,821. In other words, this is saying you sold 217 pens at $13 each. This one says you sold 13 items at $217 each. Now, if you do this problem the way I indicated previously in multiplication, where you multiply the same as you would even if the bigger number was on top. 7 times 3 is 21, put down the 1 and carry the 2. 7 times 1 is 7, the 2 you carried is 9. 1 times 3 is 3, 1 times 1 is 1, 2 times 3 is 6, 2 times 1 is 2. Watch what happens now. If I put these zeros in, I'll do it with this pen. Now for the first time, you actually can check whether you made a mistake or not, because the same 3 numbers you got here are the numbers you see over here. In other words, checking the problem this way, the multiplication shows you exactly what you did with the division. And this is very, very important to understand, because students will sometimes just do this as a blind exercise and not realize certain subtleties. For example, let's look at the problem 2,613 divided by 13. I've had students do this. 13 goes into 26 twice. I'll subtract the 26, there's nothing left. I'll bring down the 13. 13 goes into 13 once. The answer is 21. Now, if the student is memorizing, why should he think there's anything wrong with this? But here's what you want the youngster to see. If this is the right answer, then 21 times 13 should equal 2,613. Well, we know that 21 times 13 is less than 21 times 100, but 21 times 100 is only 2,100. So 21 times 13 is less than 2,100, so it's certainly less than 2,613. Now, the mechanical way that my children were taught, but it's a good way once you understand what it means, is they were taught that every time you bring a digit down, something else has to go up. So they would say 13 goes into 26 twice. There's none left over. I bring down the 1, but because I brought down the 1, something has to come up here. Well, 13 is more than 1, so I can't take 13 out of that. Then I bring down the next number, and that goes once. The right answer should have been 2001. Notice that what I did over here is taken care of automatically by doing it the method I showed you. In other words, when you put the 2 over the 6, it was 2,600. So that was 213s. When I subtracted the 213s, there was only 1 left. Not 10 left, 1 left. Now then, 13 goes into 13 once, so altogether I took out what? 213s and 1 more 13. In other words, what we did was 13 times 200 is 2,600, 13 times 1 is 13, and there was the answer, okay? Yeah, speaking of rote recipes, Abbott and Costello had their own version of a way to multiply and to divide that had audiences rolling in the aisle, so to speak. Let's see if I can reconstruct that. Abbott would do a job for Costello, and let's say he worked 7 days for $13 a day. And he would say to Costello, pay me for the time I worked. And Costello would give him $28. And said, I earned more than that. He said, no, I just multiplied 7 times 13. Now, in effect, what happened was, it would be like multiplying this way. 7 times 3 is 21, and I'll distribute the 7 with the 1 here. 3 times 7 is 21. 1 times 7 is 7. So the answer would be 28. And you look at this and you say, well, how could you do it that way? Well, that's exactly what they did. See, Costello would then explain to Abbott, look, you work 7 days for $13 each day. So I'm going to add these up. 3, 6, 9, 12, 15, 18, 21, 22, 23, 24, 25, 26, 27, 28. So all you're going to get is $28. He says, Costello, that's ridiculous. It won't check when you divide. He says, yes, it will. He says, look, 7 doesn't go into 2, so we'll try 7 goes into 8. Well, 7 goes into 8 once. 7 times 1 is 7. We subtract the 7 from the 28. We get 21. 7 goes into 21 3 times. Take your $28 and don't bother me anymore. Okay? Now, what's interesting about this problem is that this going from here to here is just as logical as the way we accept doing division, provided that this was the right way to multiply. But what happens is, in the same way that you laugh when the rote seems funny, you sort of get confused when the rote is too challenging. So at any rate, I just thought this would be something the students would enjoy, maybe you would enjoy, but let's now close by going back to our practice problem. You're going to pause the video, read the problem, do it, then come back and we'll finish up. And the practice problem says this: without actually doing the division, how would you explain to a student why she or he had done the following problem incorrectly? Just look at that problem and see how you would explain. Don't look at the multiplication per se. Just by looking at the problem, how could you tell the student why their answer couldn't be right? Look what happens. If this was the right answer, what should happen? 463 times 123 should give you 556,989. Now, 463 times 123 is certainly less than 463 times 1,000. But 463 times 1,000 is 463,000. So in that case, we would have that 463 times 123 is less than 463,000, hence it's less than the correct answer. So something went wrong here. And again, what went wrong is, let's do the problem the correct way, meaning the way we understand the adjective noun theme. When we put the 1 over here, the 1 really stood for 1,000. 1,000 463s is 463,000. When we subtracted, we got 93,989. Okay? Then we saw that 463 goes into 939 twice, but by putting the 2 over here, that was 200. And 200 463s are 92,613, and that's 1,389. And from 1,389, all you can do is take out 3 more. And so the correct answer is 1,203. And what happened over here is we omitted a 0. And the way to get around that is to do it, if you want to do it mechanically, the way my children were taught. Every time you bring down a digit, something has to go above it. And since 463 is smaller than 138, we can't take any bundles out, so we just have to have a placeholder. Then we bring down the next digit. And the answer is now correct. At any rate, I think this should conclude what we're doing for today, and I'm going to look forward to seeing you again next time.